Hello everyone, hope this video finds you well. We are going to be discussing in this video the inverses of functions. My only purpose really in this video is to provide you with a little bit of background information, background concepts of what an inverse really is. There's some very important things that you should know about inverses. They don't necessarily help you solve the algebraic mechanics of finding an inverse, but it's very important that you have a grasp of these background concepts. Okay, so there are many different ways that you could actually define what an inverse function is. Some of them are really complicated and difficult to work your way through. I think a fairly simple way is to say that an inverse function is a function that undoes everything that another function does. Okay? In other words, if f, let's call a function f, if f takes an x value and turns it into a y value, then the inverse of f, which we write as f negative 1, that function takes that y value and turns it back into the original x. Okay? That's what I mean by undoing another function. So we'll have a couple more examples of that a little bit later here. By the way, it's important to note here that that symbol f negative 1 does not mean f to the negative 1 power. It's just a symbol like f with a little superscript of negative 1, and that means the inverse of the function called f. Okay, let's take a look at an example of one on a graph. Here's a perfectly nice little linear function, f of x. You could probably figure out what the equation of that function is with a little bit of effort, but I want you to think about this function in terms of inputs and outputs. Okay? You got x values turning into y values by this thing called f of x. For example, there's one input value of negative 4 and it's been turned into a negative 1. So that's why the point negative 4, negative 1 is on this graph. So there's the input, negative 4, the output, negative 1. And there's lots more points, obviously. Negative 2 got turned into a 0, or the input of 0 got turned into a positive 1. And then there's a 2, 2 up there. Okay? So if an inverse of f takes that output and turns it back into the original input, that would mean then the point negative 1, negative 4 is on the inverse of f. So there it is, and if I did a couple more points, the points that I've illustrated there, that would mean the inverse of f would take a 0 and turn it into a negative 2. It would take a 1 and turn it into a 0, and then there's that still kind of funny 2, 2 point up there. And in fact, if you graph those points, you can see they're all in a line, just like f is in a line, that there's the graph of the inverse of f right there. And this brings up a very important concept about the graphs of a function and its inverse. When you look at them both at the same time, they are always symmetrical around this line y equals x. Okay? Very interesting idea. And then you can see why this point 2, 2 up there is on, well, it's clearly on the line y equals x, where x and y are the same number. It's also, and if it's a point like that on f of x is going to be the same point on the inverse of f. So kind of an interesting thing there about the graphs. The other extremely central idea to functions and their inverses is this thing that I call the swap. All right? In fact, this idea is so central it could almost be a definition of what an inverse really is. And what I mean by the swap is that a function and its inverse swap their respective domains and ranges. Okay? This is a critical concept about inverses, that they switch their x values and y values. The domain and range are swapped from a function to its inverse. Let me just illustrate that with a little diagram here. If you have some kind of a function f of x, let's say, and there's a picture of all the x values, okay, that's its domain. Those x values are turned into some y values by the process of f of x. Okay, so there's the domain and there's the range. Now the inverse of f of x, all right, takes those output values of f, in other words, those now become the input values into the inverse, and the outputs are those exact same x values that we started with. Okay, of course, we are talking about the inverse function of f negative 1 of x, and that means that those actually are called x's and y's, but it's the same numbers. For example, if I know that f of 3, for example, equals 5, then that tells me that f negative 1, the inverse of f of 5, is equal to 3. This is actually really math power here. This is powerful information. So that if you know two functions are inverses of each other, you really only have to know the domain and range of one of them, because that's automatically reversed for the inverse. So that's useful information. So here's a little summary then of some of these background ideas, and there are more ideas, very interesting things that you're getting into with some of the exercises that you're practicing for this. But here's just kind of a summary of the basic ideas of inverses. One way to define an inverse is it is a function that is undoing another function. Okay? Another main idea here is the symbol that we use. That f negative 1 of x means the inverse of f of x. Don't confuse it with f to the negative 1 power. It is not the same thing. The other idea is that the graphs of a function and its inverse are always symmetrical around the line y equals x. This is an important idea about the graphs. In fact, it's a way that you can actually even check to see whether two functions are really inverses of each other. Are they really symmetrical around that line y equals x? If they're not symmetrical, then they're not inverses. It's simple as that. The last and most, maybe not the most important, but a critically important thing about inverses is that a function and its inverse swap their respective domains and ranges. In fact, like I say, that could almost be a definition of what an inverse is. It's a function that swaps the domain and ranges with another function. Okay, that's about it. Hope that wasn't too painful, and be looking for the question online. Okay, bye-bye. Hi there, I'm glad you tuned in one more time, and this video will actually be about something called a one-to-one function. But before we get into that, I want to recall for you what the definition of a function is, okay? So we are talking about inverses here, keep that in mind, but a function is a relationship between input and output quantities like x and y, such that for each input value there is exactly one output value. Okay, so that's the definition, the formal definition of a function, and many of us get a little intimidated by such high academic language there. And we also have a very easy way to think about a function, which is called the vertical line test, right? And you remember that if you draw a function and you take a look at that function, and if you can pass a vertical line through it and it never crosses the function more than once, it passes. That is a function, okay? So that thing that I just drew there, that passes the vertical line test. Now, let's get back on track here, and I want to talk about one-to-one functions. Okay? First off, the reason that we care about one-to-one functions and their relationship to inverses is that a one-to-one function is a function whose inverse is also a function. Okay, so that's kind of why we care about them in relationship to inverses. Any function whose inverse is also a function is called a one-to-one function. So that we have this definition of a function. For each input, there's exactly one output. And the definition of a one-to-one, the formal definition of a one-to-one function, is a function. So it meets that first part, but it's a function that's for each output value, there was only one input value. Okay? Now again, we're just kind of layering on this high academic language here, and if you are confused by this, don't worry. There is something easily graphic and visual for one-to-one functions, and it's called the horizontal line test. All right? Here are a couple of functions that pass a horizontal line test. Y equals the square root of x there on the left, and you can see a horizontal line only crosses that function in one place. And so therefore, it's a one-to-one function. On the right, y equals x cubed. A horizontal line only can cross that function at most one place at a time. So that also is a one-to-one function. Here's another one, y equals x squared. That's a parabola. Now think about a horizontal line crossing a parabola. That's right, it's going to fail. A parabola is not a one-to-one function.
A parabola is a function, but it's not one-to-one. Okay, so I hope that illustrates the idea of the one-to-one function and its relationship to inverses. And as usual, there is more to the story, so stay tuned, keep your ears open, and now go do some math.